Here's the periodic table, and I'm just going to label this section S for the S sublevel. This section is the D block for the transition metals. Over here we have the P sublevel, and down here we have the F, and it's going to basically branch off right there. We're going to discuss the periodic properties or the patterns that we can see in the periodic table. Let's start with the most important one. Probably is going to be atomic radius, and this is just the size of the atom. It's going to be really small towards this right side over here, and then it actually gets a little bit bigger towards this side, and then as we come down here it also increases and gets really big down there. Now the size is really important because, well, the small elements are actually going to be very stable. So the larger that it gets, the more unstable it becomes, the more reactive it gets. And so you kind of get this idea of metallic character, where you have a tendency to lose electrons. All right, and this is what reactivity is. So this is reactive. So atom size has a very big impact on this. There seems to be 3 ways to increase the atom size. The first one is to add electrons to a higher N level. So as you see that we're going down this direction, we're going to be going through the periods, so through different N levels. And as you increase down there, that's one of the best, most strongest ways to increase the atom size. Another way is by having less protons. So as we go this direction, because we're getting less protons, we should be increasing the atom size. And that's a very good way to increase the atom size, but it's not as powerful as the first method. And you can really think of this because here's your positive nucleus, and if you got an electron out there, well, it really just depends on the strength of this positive charge to know how attracted is that electron to that. So if you have less, obviously the electron can go out pretty far. And it also has to do with sublevel splitting. Sublevel splitting is when you add electrons into the same sublevel, and well, you'll get higher repulsion. So this electron wants to go that direction, this one wants to go that direction away from each other, and so therefore it will just expand the size of the atom. So higher electron repulsion, and that requires more energy. Now there's 2 ways you can add an electron to another sublevel. Either you use a new sublevel entirely, and what I'm talking about sublevels is going to be like S, P, D, F. So you could use a completely new letter, or you put it in the same sublevel. Both of these are going to cause more electron repulsion because, well, I mean, it's the same general area. So, even if you put another one in a different sublevel, it's still going to be kind of near. So you'll have more repulsion there. We mentioned energy before. Let's take a look at Coulomb's law. In fact, we'll define it for E lattice. This is the lattice energy, or we could say the ionic bonds that are in a solid. If you add up all the energy in those bonds, it's going to be equal to the lattice energy. You could calculate this by taking Q1 times Q2, and there's the absolute value, and then we're going to divide that by the atomic radius. Let's do an example. We'll go 2 plus multiplied by 3 minus. Those are going to be 2 charges you might find on an ionic compound. This is only for ionic compounds. We'll divide that by the atomic radius, but the thing is we don't really know what that atomic radius is. We'll just eyeball it. This is like the cation and the anion right here, so you can take the distances in between those two. This is the atomic radius. It's going to be exactly touching them like this, not smushed together like a covalent bond would be. This is an ionic bond. So if you don't know the radiuses, you can try to look at the trend on the periodic table and do a comparison test. But this is going to have an impact on the boiling point of stuff. So if you have a high energy, the lattice, then you're going to have a higher boiling point because there's more energy holding this stuff together. You're going to need more energy to break it apart. So as you can see, the size here, the atomic radius increases from right to left, top to bottom. This also kind of goes along with the metallic character of the atom. And, well, it turns out that the D's are actually going to be the smallest of all of the atoms. And the reason you start getting this F thing, this F block that you can open up here and get so many more atoms in there, is because when you have a larger atom, it fits more electrons. And so you have a bigger circumference, and so as you get bigger and bigger atoms, you can start to add more electrons in, and so now you get more different configurations, and now you have another block down there. Now we know the atomic number is supposed to be Z, but there's another number, Z effective, which is going to be the atomic number minus the number of shielding electrons that are guarding a nucleus. Let's start by drawing a little nucleus right here. And then we can start to imagine there would be some electrons over here, and you get further and further away. Well, the first one over here is going to be pretty strong. It's going to be a nice shield. And you can think that this one right here is not going to have such a strong effect, because look, there's a repulsive force of that one. So this one's going to be not as affected by that nucleus. And over here, this one's going to be so weak out here, it's going to be easy for this to even come off. So basically, the Z effective is taking into consideration the electrons that are blocking off that nucleus. Usually this would be just straight up Z, but we're subtracting these shielding electrons. So this one's going to be like the S, this is the P, this is the D. And in order to count those, all you need to do is take a look at the noble gas that is that you'd use in the shorthand configuration for it. And then those would be the shielding electrons. But wouldn't it be weird if I said that this was 2s? Huh? And that this was 1s? What? How is the 1s further than the 2s? How is the 2s closer to the nucleus? It's supposed to be the opposite way, right? Well, that's the concept of penetration. And basically, if you have a higher N, but that N is closer to the nucleus, then you have the penetration, essentially. And the reason is because, well, remember the Schrodinger equation? We were taking a look at, like, the probability of from R going from 0 all the way to some certain distance from the nucleus. We'll call it infinity, because technically it could be found anywhere. This goes to infinity. But this is a probability distribution. And so naturally, there's going to be some times when the higher ends will be closer to the nucleus than the smaller ends. It's probability. So Z effective is essentially just going to make the same trend that the normal Z would be. That would be this direction. So here's your Z effective. And this is going to go along with mass and density. Those are going to be two things that are going to follow the same trend. So we might as well put them on the same arrow here. Now the size of the atom and the Z effective are both going to impact electronegativity. And this is when the atom attracts electron pairs. It really wants to grab those pairs in those electron groups. So essentially, the atomic size and the number of protons are going to be the biggest factors in electronegativity, and it's just going to affect the polarity of bonds. We've already went through this little chart in another video. The trend of electronegativity is going to be this direction, along with the protons increasing. But at the same time, we also have the size decreasing to a very small amount, and also it would be going this direction because the size is more important when we're talking about electronegativity. If it's really close, the electrons are close to that nucleus, the nucleus will have a stronger pull on the electron, and so it will want to attract that. Ionization energy is all about removing electrons from the atom in its gaseous state. Let's take a look at the cation, which is supposed to be positive. But how did it get positive? Well, we started with a neutral charge, and then we subtracted the electron from it. This is a negative charge, so we subtract negative, it becomes positive. We're going to need to pull this electron from a high energy orbital because we want to get rid of the energy. We want to reach a low energy configuration. So we're going to pull that electron away from the high energy, and then we're going to go ahead and create an anion, which is the neutral plus the electron. We'll go ahead and give that electron to the anion, but we're going to add the electron to the lowest possible energy orbital. And so we're trying to achieve the state of lowest energy. We're trying to reach this thing called isoelectric. It's the noble gas structure. So let's say you'd have magnesium 2+, and also the oxygen 2-. Both of them are trying to achieve the neon gas structure. This is the noble gas configuration that has the least amount of energy. We can usually tell what electrons are being pulled from these by looking at the shorthand configuration. Let's take a look at Mg, which would be neon, and then you have the 3s2, and you could try oxygen, which would be He, and you have your 2s2 and a 2p4. So you can clearly see that if we're losing 2 from here, it's going to be those two. We have to keep an eye out on ionization energy levels. So we have level 1, level 2, level 3. This is essentially the number of times that we have ionized a particular atom. So you might pull from the S, and then you might get another one from the S. So if you try pulling both from the S, you'll kind of get a low, difference between those two. But all of a sudden we want another one, so you'd have to kind of reach into the p orbital here. And of course, you're going to get a large jump of energy there if you want to open up a new sublevel. So like you can keep working with your same sublevel if you want, but as soon as you get to another sublevel, you'll see a big jump in energy. So we kind of have to be careful there, because that will basically determine whether you're going to pull from the same sublevel or from a lower sublevel or a higher sublevel. So you have to keep track of the ionization energy. Before the next example, let's look at the trend of ionization energy on the periodic table. It will be this direction. So this is ionization energy. And it will also go this direction. And it's going to go along with electronegativity because, well, if something wants the electrons, then it's going to be harder to pull away from them. Now let's compare some ionization energies between nitrogen, oxygen, beryllium, and boron. If we look at the electron configurations of these things, it's going to be like S2p3, whereas over here we have S2p4, and here would be an S2 versus here it's an S2p1. So you can immediately see that these guys are in a very stable position. So it's going to require more energy to break them than these ones over here, because here you have a free P, and here you'd have another free P. So we're going to put that this energy is going to be a higher ionization energy to break those, and a lower ionization energy over here. And that would go against our trend if we look at the periodic table. Transition metals and lanthanides and actinides have their own little rules. The transition metals tend to lose S electrons before the D, and the lanthanides and actinides tend to fill the F after the D1. So we can compare some metals like chromium and molybdenum and tungsten and palladium and platinum and copper and silver and gold. This is how they appear in the periodic table. These ones over here, all their structures are going to be S1D5, which goes against where they would be S1. What the heck? And over here, you get an S1D10. So you're taking one away from the S to fill that up. Over here, you get these two being, this one's S0D10, and this one is S1D9. We also have cerium and thorium, which would be S2, F1, D1. But first you'd fill the D1, and then you're going to put the F1 right in between as you continue them. The last trend is going to be electron affinity, and this is the change of energy when an atom in its gaseous state gains an electron. Usually, the energy would be a negative because we're trying to achieve a lower energy state. We're trying to lose the energy. This would be an exothermic process when we're gaining electrons. But sometimes that change could be positive. If we're already in a stable configuration, then well, it's gonna suck to gain more energy, more electrons. So it's actually gonna gain energy and make it a more chaotic state because it's already at its minimum energy. If you start messing with it, it'll just make it worse. Let's take a look at the general trend of the electron affinity. It's gonna be this direction. Electron affinity. It goes along with electronegativity because if something wants more electrons, attracts more electrons, is going to want to lose that energy and get to a less energy state. So it goes along with that. And it's actually negative numbers, increasing negative numbers to the right, although there will be a counter trend at some point because of the stable configurations that you'll encounter along the way. And it also goes up here on the periodic table. So these are all the different trends that we can notice in the periodic table.